In the last section, we discussed that the sampling process was in itself a variable process, and that because it was a variable process, it would have its own distribution. In this section, we're going to talk about how we can use information from that sample and the distribution that we would get from that process to come up with a way of estimating a value for the population mean. Not only will we do a specific estimate of the population mean called a point estimate, we'll also come up with a range of estimates within which we think the population mean may lie, and that will be a confidence interval. So the first objective will be to obtain a point estimate for the population mean, then talk about a distribution called the student's t-distribution, how we can determine a t-value, and construct and interpret a confidence interval for the population mean, and find the sample size needed to estimate the population mean within a given margin of error. Well, what do we mean by the word point estimate? That means, based off of the sample information we have, what do we think might be an estimate for the population mean? So a point estimate is a value of a statistic that estimates the value of a parameter. In this first case, the sample mean x bar is a point estimate of the population mean. Each time we take a sample and we look at its average, we're coming up with an estimate for the population mean. So for example, we'll go back to our penny example here, and we will take a sample of, it looks like 17 randomly selected pennies, and if we take the average of that, we would come up with an average value of 2.464. That's the sample average. So our point estimate of the population mean is 2.464 grams. If you take a different random sample, you will most likely come up with a different point estimate for that population mean. Because we have different point estimates, what we would like to do is take into account the variability and come up with the most likely scenarios for what range of values the population mean might lie in. In order to do that, we have to introduce something called the student's t-distribution. Student's t-distribution is a distribution that looks much like the normal distribution, than it is bell-shaped. The difference is that it's a little fatter in the tails. There's a little more going on away from the center of the distribution than there was in the normal. And we'll look at some examples here in the coming slides. But what I wanted to show you was, again, because of this nice shape, it is symmetric about its average, and just like with the normal distribution, we can come up with a standard t-distribution that we can center around 0. So it will be symmetric around its mean, and standard deviation will still be our step size. The difference is that with the t-distribution, it depends on the number of things in our sample. So each sample size will have a slightly different t-distribution. Rather than doing a lot of tables, we're going to do a single table that gives us the information that's most often used from the t-distribution. With the normal curve, we had problems where we looked up a z-score to come up with a percentile. We also had some problems at the end where we started with a percentile and we came up with a z-score. With the t-distribution, that's going to be the approach we're most often going to need. We're going to have some percentile that we need, or some percent of the time an event will occur, and we will want to find the t-value that goes with it. So the structure of this table is a little different than the normal. Down the side is what's called the degrees of freedom, and that number is related to the sample size, and we'll talk more about how it relates later on. Across the top are different percents of area that are in the right-hand tail. So this little shaded region corresponds to values across the top. So let's say I had a situation where I had 5 degrees of freedom, and I wanted to know what the t value was that went with a 5% area in the right-hand tail. Well, I have 5 degrees of freedom, means I'm going to be in the 5 row, and I want 5% to be in this upper tail, so I'm going to look at the 0.05 column, and I see a t-score of 2.015. So a t-score of 2.015 corresponds to 5% of the area being in the right-hand tail when I had 5 degrees of freedom. We'll do some more examples working with this later on, but for now I just wanted to give you an idea of what the t-table looked like, and that it is similar to the normal table in shape, but it's a little thicker in the tails. So now we're going to state some properties of the t-distribution. First of all, the t-distribution, if I want to standardize it, I'm going to end up, it's coming from using sample information. And so I'm going to be working with sample information and standardizing things from the sampling distribution of the mean. Well, remember that for something with for the sampling mean, the distribution tends to be approximately normal. And we get our standard score by looking at how far our measurement is away from the mean and dividing by the standard deviation. In the sampling distribution, our estimate for sample standard deviation is S. So our estimate of the standard deviation for the sampling process is S over the square root of n. So we can get a standard t-score by subtracting off the mean and dividing by S over the square root of n. We say that t follows a student's t-distribution with n-1 degrees of freedom. In other words, the number of degrees of freedom is the sample size minus 1. Why isn't it n degrees of freedom? Well, we're using x bar, which is a parameter or a statistic to estimate a parameter. We're also using S, another statistic, to estimate a second parameter. That means we're going to lose a degree of freedom. We use x bar in the calculation of S, so that means we lose some freedom in our choice of values. So we have n-1 degrees of freedom. So for example, if I look at a comparison and I take 1,000 simple random samples of size 5 from a normal population with mean of 50 and a standard deviation of 10, and I compute the z-score and the t-score, we'll see similar shapes, but the t one will be a little bit broader than the z-score is. Okay. Now again, here we're assuming that sigma is 10. With the t part of it, we'll be using the sample standard or the sample means to estimate the sample standard deviations. So if we look at that 1,000 random samples, we see a pretty nice bell-shaped curve there that's pretty close in. However, if I look at the histogram for t, it's still moderately bell-shaped, but notice that there are more extreme values. We're not just kind of stuck within -3 to +3 now. We can go a little bit further out with the t. So there's more area in the tails. So kind of some comparison for the standard normal curve. Z is symmetric and bell-shaped with the center at 0, and almost everything lies between -3 and +3. However, for the t distribution, while it is symmetric and bell-shaped with a center around 0, it does have longer tails. It is unlikely that t follows the standard normal distribution. The additional spread in the distribution is attributed to the fact that we use S to find t instead of sigma, because the sample standard deviation is itself a random variable rather than some fixed constant such as sigma. We will have more dispersion in t, and we saw that in our two pictures. So kind of some more conclusion and properties. As we saw from the table I looked at, the distribution of t is different for different degrees of freedom. It is centered at 0 and is symmetric about 0. It is a distribution, so the area under the curve is 1. Because it's symmetric about 0, half of the area will lie to the left and half of the area will lie to the right. And just as with the normal curve, I will always have a positive probability, but the further out I go, the smaller that probability gets. So the further away I go from 0, the probability will get smaller and smaller and smaller, but it will never actually touch the axis. The area in the tails of the t distribution is a little greater than the area of the tails in the normal. And again, it's because we're using S as an estimate of sigma, thereby introducing further variability into the statistic. However, as the sample size increases, the density curve gets closer and closer to the standard normal curve. This happens because as the sample size increases, the values of S get closer to the values of sigma, and so our central limit theorem says that this will be approximately normal. And here's the picture I said we would revisit a little bit later on, or look at later on. The blue curve is the standard normal curve. If I look at the t distribution with n equals 5, that's the orange curve. You can see that it's bell-shaped, it's still centered around 0, but it's a little more spread out than the normal curve is. There's more area in the tails. With n equals 15, I still have a nice bell-shaped curve. There's still more area in the tails of that t distribution than there are with the normal, but notice that it's getting closer to that normal curve. If I were to look at t equals 30, it would be much closer. So as n increases, the t distribution will get closer and closer to the normal distribution. In general, if we have a sample size greater than 30, we say that the distribution's normal enough that we can use the normal distribution. With that said, the problems that you have in your homework, whenever the t distribution can apply, you will use the t table, regardless of what the sample size is for n. The reason that we do that is that most of the time you'll be working problems with this, you may be utilizing a computer program to do the calculations for you. The computer program will utilize the t distribution whenever we're incorporating both sample mean and sample standard deviation. So in order to get you used to that, your homework problems will always do that. In practice, you may not have a computer program near you. You may only have a calculator and need to be doing a rough estimate, in which case, if the sample size is bigger than 30, you can use the standard normal curve to do an approximation. So now we're going to determine t-values. just like we had before when we talked about Z alpha being the z-score for which alpha percent of the area lay to the right of that value, we can talk about T alpha. T alpha is the t-score such that alpha percent of the area lies to the right of that value. So if I look at t sub 0.05, that means I would want the t value where there was 5% area in the right-hand tail. Or in other words, I'd have 95% to the left, or 1 minus alpha. So I'd be looking, if for t sub 0.05, means I'm looking for the 95th percentile of that t distribution. I want 5% to be to the right. Alpha represents the area to the right in that tail. So now let's see if we can find a t-value such as the area under the t-distribution to the right of the t-value is 0.2, and we assume 10 degrees of freedom. So in other words, I want to find t sub 0.2 with 10 degrees of freedom. So we're going to go back to our table, and again, what we're looking at, t sub 0.2 means I want 20% of the area to be to the right of that t-value. So let's go to our table. Oh, I don't have a 0.2 in my table. So if I were to come up with t sub 0.2 on 10, I would look in the 10 row. I seem to have lost my cursor here. Give me a second to find it. There we go. I would go to the 10 row, and I would look in the 0.2 column. Well, I don't have 0.2, so it's going to be somewhere between 1.372 and 0.7. If I had a 0.2 there, I'd be able to find it. Because we have a computer-aided program, we can find out that the t-distribution actually has a value of 0.879 when I have t degrees of freedom and I want 20% in the tail. So that t sub 0.2 would be 0.879. Excuse me. Okay. So now we're going to construct and interpret a confidence interval for the population mean. Again, this goes back to part of the reason why we're interested in this t-distribution, is we've come up with a point estimate for the confidence interval, or excuse me, a point estimate for the population mean by taking a sample and looking at its average. Based off of that information, though, and the t-distribution, we can come up with a range of estimates called the confidence interval. In order to come up with a confidence interval, we would need to have some requirements met before we can move on. First of all, the data does need to come from a simple random sample. Our sample size does need to be less than 5% of the population size. And we need for the population to be normally distributed or the sample size to be large. And a 1 minus alpha 100% confidence interval for mu then is given by x minus t alpha over 2 times s over the square root of n. The upper bound is x bar plus t alpha over 2 times s over the square root of n, where t alpha is the critical value with n minus 1 degrees of freedom. Okay, that's a lot of notation. Let's try to make it a little more sense by putting in some specific values. Let's say I want a 95% confidence interval. Well, 95% confident means there's 5% uncertainty there. So that means alpha would be 5%. Because I'm looking at a confidence interval, I want it to be symmetric about the mean. So that 5% uncertainty is split up equally between the two ends. So we're going to have 2.5%, 0.05 over 2, in each end. So we're going to find the t-value where there's 2.5% of the area in each tail. And I'm going to add on that number of steps where the step size is s over the square root of n, and I'm going to subtract off the number of steps where the step size is s over the square root of n. So that gives us our confidence interval for the mean. So for example, well, let's go ahead and do an example here. Let's suppose that we have the following. Let's suppose that we have that x bar is equal to 27.6, that the standard deviation is 3.2, and we have n equals 16. And we want a 95% confidence interval for the population mean, mu. Well, again, what that means is we're going to start with our mean of 27.6, and what we want to do is find a t-value here such that we end up with 95% of the area under our t-curve being between some two numbers. Well, let's call it x1 and x2, or lower and upper. Because I've got the middle 95%, that means I have 2.5% here and 2.5% there. So if I take a standard or a t distribution that is centered around 0, and I want that to be 0.025, I want the value here that's t sub 0.025 with 15 degrees of freedom. Remember, n equals 16, so that says that there are n minus 1 equals 16 minus 1, or 15 degrees of freedom. So if I go to my table and I go to 15 for my degrees of freedom, so that's the 15 row, and I go to the 0.025 column, that's 2.131. So I know that t sub 0.025 comma 15 is 2.131. The notation that we have that we use is we'll put t with a subscript of alpha, whatever the value was that we were looking at, percent that's going to go in the tail, and we'll use a comma and then we'll put the degrees of freedom with it. So this tells me which column to look in. This tells me which row to look in. I know I wanted the t-value in the 0.025 column along the 15 row. So now we know that our lower end is x bar minus t times s over the square root of n, which in this case is 27.6. Let's go back up here. S was 27.6. Or x bar was 27.6, and s was 3.2, and n was 16. So we're going to do 27.6 minus minus 2.131 times 3.2 over the square root of 16. And if we finish that calculation, we end up with 27.6 minus 2.131 times 3.2 divided by the square root of 16, which is going to give me 25.8952. And if we want the upper, that's going to be x bar plus t times s over the square root of n, which is 27.6 plus 2.131 times 3.2 over the square root of 16. And calculating that, we come up with 29.3048. .3048. So our confidence interval, our 95% confidence interval, is 25.8952 to 29.3048. So what does that mean? Well, that means that we are 95% confident that the true mean lies within this interval. Does that mean there's a 95% chance that the mean lies in that interval? No. The true mean is some fixed number. We do not know what that value is. All we're doing is estimating it. The true value will either lie in there or it won't lie in there. What the 95% refers to is our level of confidence in the methodology we used. What do we mean by 95% confident? Well, let's take, for example, a sporting event where I have two teams and I have looked at the abilities of the two teams and I've decided who's going to win. The outcome of that game is either the team I picked to win will win or they won't win. There's not a 95% chance they will win. They'll either win or they won't. My level of confidence, though, is how strongly or how confident am I that they will win that game. So how confident am I that I'm right? So let's look at an example let's say we have a normal distribution with a mean of 50 and a standard deviation of 10, and we took samples of size 8, and when we did the sampling process 30 times, and we calculate a confidence interval from those samples. And let's see what happens. Notice that not every interval that I get will contain the mean of 50. This 8th interval does not contain the mean. In each one of these cases, either the mean of 50 lies in the interval or it does not lie in the interval. There's no 95% chance it lies in the interval. It's either there or it's not. The 95% comes from how confident are we in this process. So in other words, if I were to continue this process over a very long period of time, about what percent of the time would the intervals contain the true population mean? In this case, we see that 28 out of 30 actually contain the population mean. Okay, so let's say we're going to find a 90% confidence interval for the true mean of the weight of pennies using our sample that we had of size 17. And if we do that, then we can come up with a t-value of 1.746. Where does that come from? Well, I'm going to go to my t-table. There were 17 values in my sample, so that means there are 16 degrees of freedom. So I'm going to go to my 16 row. I know I wanted the 90% confidence interval, which means there's 10% I'm not confident, putting 5% in each end. So I want to go to the 0.05 column, and I see that under that I get a t-value of 1.746. So I get a t-value of 1.746. So that's the number of steps I need to be away from the mean. So I plug in the standard deviation over the square root of n. So I get 2.464 minus 1.746 times 0.02 over 17. And I can go out positive 1.746 steps of this size, giving me 2.472. So I'm 90% confident that the mean weight of pennies lies somewhere between 2.456 grams and 2.472 grams. The last objective in this section is to talk about the sample size needed. So in order to do that, I want to look at a picture and kind of help derive a formula. I know that my confidence interval is centered about x bar, and on one side it's x bar plus t times s over the square root of n, and we get x bar minus t times s over the square root of n. That's what I use if I have to estimate the sample standard deviation. So if we don't know sigma, we use that. Well, if n is large enough, we can use a z-value. So if n is large enough, we can use Z instead of T. If I look at this distance, this is called my margin of error. So, in other words, the error is equal to T times S over the square root of N, which is approximately Z times S over the square root of N. So if I want to solve for N, that would mean then that the square root of N is S times Z over error, which gives me then N is S times Z over the error squared. So given some Z value, I can approximate the sample size needed by taking S times Z and dividing by the error and squaring it. Another way I could do it is look at N is 2S times Z over the width squared. Right? Our interval is actually, so this would be the width, would be 2 times our margin of error. So for example, we then get this formula, and let's say we wanted to be within 0.005 grams. So we wanted our margin of error to be plus or minus 0.005 grams. And we knew that sigma was 0.02, and we wanted 99% confidence. Well, on the Z table, we get a Z-score of 2.575. That would give me a value for the Z-score where 0.5% lay to the right of that value. And we then would put that into the formula, and we would come up with 106.09. We can't have 1/2 of a value, so we have to have 107 objects in our sample. Well, that concludes our discussion on this section.